Hello and welcome back. In this video we will start section 7.2, which is on trying to estimate population means rather than population proportions. So we're going to be looking essentially at averages now. And if we want to estimate a population mean, one way to do that is to just give a point estimate. As in, we find a sample mean and we say, oh, the population mean is probably going to be close to the sample mean. So if I had to take my best guess, I would just use the sample mean to estimate the population mean. Now, giving one exact value is maybe a bit misleading, so maybe it's a little bit better, like we saw in the last section, to give a range of values, and we'll give a confidence interval, a range of values that we are quite confident will contain the actual population mean. Essentially, we're just going to be constructing these intervals today, and let's go through some notation and requirements for our estimates to be true. So the population mean we normally have as mu, and the sample mean is going to be x bar. X is normally the variable for each individual data value, and x bar is going to be the mean of those values. S is going to be the sample standard deviation. N is the size of the sample. And E, just like last time, is going to be the margin of error. And if I skip ahead for a second, the confidence interval itself is simply going to be x bar, so the sample mean, plus the error minus the error. So anywhere between those two values is going to be what we'll be confident the population mean will be between. So when can we use the statistics that I'll be talking about? Well, first of all, our sample has to be a simple random sample. We can't go out and collect a sample that's not very random because we're not going to get a very representative sample mean. And due to the fact that we'll be using normal distributions, we will need the population to either be normally distributed to begin with, or the sample itself, we need to take a sample of at least 30. So as long as one of those two things is true, then our sample means are going to be normally distributed, so we can use the mathematics that we're going to discuss. So one of these two things needs to be true. If neither of these two things are true, if we're looking at a population that's not normally distributed and we don't have very big samples, then we'll have to use other methods, which will be discussed later in the book. Just as a quick aside, sometimes this interval, we can write it as an interval of numbers. We can write this as the numbers from x bar minus e to x bar plus e, so it can be written as an interval like this, or you'll sometimes see x bar plus or minus e, just sort of giving the two endpoints of the interval, x bar plus e and x bar minus e. So all three of these things mean the same thing. Let's look at our formula for the margin of error. And this is our formula. And there will be a couple things that we'll notice here. One is that we have t sub alpha over 2 rather than z sub alpha over 2, and I'll explain t in a second. But essentially it comes from this over here. And when we look at s over the square root of n, this is just like a few, I think it was in the previous chapter when we were looking at normal distributions, when we were looking at sample means, when they are normally distributed, their standard deviation is normally sigma over the square root of n. And this is going to be the standard deviation for sample means. However, we're trying to estimate mu, the population mean. So if we don't know mu, we probably don't know the population standard deviation. So we don't know sigma here. So we'll just have to use our best guess, which is going to be S, which is our sample standard deviation. So again, we can't use the population standard deviation, we can only use our sample standard deviation. And because we're using our sample standard deviation, and sample standard deviations are not perfect estimators of the population, they are biased estimators, we have to compensate for that a little bit. So instead of using a truly normal distribution to come up with this corrective factor out here, we'll have to use a different distribution. And you can see at the bottom of the screen, this is going to be called a student t distribution. So this t distribution is what we'll use out front. A couple more little bits here. So the confidence level is exactly the same as what we saw before. It's going to be something that's close to 1, normally say like a 95% confidence level or a 99% confidence level. And we'll use that confidence level to come up with t. The more confident we want to be in our answer, the bigger range we have to give so that we're more confident the mean is actually inside of that range. If we don't need to be as confident, I can give a smaller range. There's a bigger chance the mean is outside of that range, but I can be more precise. And in order to come up with this critical value, this relies on what's called the degrees of freedom. And the degrees of freedom is essentially how big of a sample we're using. The bigger the sample, the more degrees of freedom, the closer everything is going to be being a normal distribution. The smaller the sample, the less normal the distribution will be, so we'll have to adjust our t distribution accordingly. So we just need to take into account how big of a sample we're using, and this is just the degrees of freedom. So instead of using a perfectly normal distribution, we use a student t distribution, and it's a nearly normal distribution, and it describes essentially how far away it describes the distribution of the sample means, but it describes that distribution with respect to the sample standard deviations as opposed to the global, the population standard deviation. So again, all we're doing is, because we don't know the population standard deviation, we just have to fudge a little bit. So this isn't a perfect normal distribution, but it's close. So essentially, what do I mean by close? Well, it's still bell-shaped, but it's going to be flatter than the standard normal distribution. So when we're looking at t's, it's going to be a bell shape, but it's going to be a bit flatter than the normal z distribution, the normal distribution. And again, the bigger the sample that we have, the more normal t looks, because with a bigger sample, we will be closer and closer to a truly normal distribution. So we just have to take into account how big our sample is when we want to calculate our t values. And then the degrees of freedom is always going to be the size of the sample minus 1. And just to sort of illustrate this a little bit, when we look at what happens to the t distribution, well, the t distribution is nearly normal, as in it looks like a normal distribution, but it's just off by a little bit. And in particular, if we take smaller sample sizes, if the degree of freedom is smaller, it's going to be even flatter. It's going to be flatter and flatter and flatter the smaller sample size. The bigger the sample size, the bigger this sort of bell shape in the middle is going to be, the closer to a normal distribution. So bigger samples leads to more accurate statistics. And just like last time, we have our distribution, and what we want is going to be this t value, which we call t sub alpha over 2. What does this refer to? Well, the area in the middle is going to be 1 minus alpha. So our confidence is going to be that the population mean is going to be within 2 values, and this is our confidence. This is our way of determining that our confidence interval. So 1 minus alpha is going to be the area underneath the curve in there, which means that because the t distribution is perfectly symmetrical, just like the z distribution, the area outside here is going to be split evenly, alpha over 2 and alpha over 2. So when we see t sub alpha over 2, this is exactly what we mean. It's going to be the t-score, not the z-score, but the t-score that corresponds to having an area of 1 minus alpha in the middle. So alpha over 2 is to the right, and then alpha over 2 is to the left. So over here we'll just have the same t-score, but negative. So let's go through and calculate a t-score, this t sub alpha over 2, for a 95% confidence interval for a sample of size n is equal to 12. So the first thing that we'll want to do is calculate the degrees of freedom. And in this case, it's just going to be n minus 1. So this is 12 minus 1, which is 11. Okay. So this is the degrees of freedom. And if I go to StatCrunch, we can pull up a t calculator rather than the normal calculator. So if we go to Stats, to Calculators, and rather than going to the normal distribution, we'll go to the t distribution. And when we pull it up, you'll notice that it looks a lot like a normal distribution. And we can input our degrees of freedom. So we want our degree of freedom to be 11. And coming back here, we want 95% confidence interval. This means, 0.95 is going to be the same as 1 minus 0.05. So alpha here is going to be 0.05. So when I look at my distribution, in the middle, let me just draw a new picture here. In the middle, we'll want 95% of the area. Off to the left and to the right, we'll want 5% in total, which means that if I cut that in half, this will be 0.025 to the left, to the right, and 0.025 to the right. So coming back to our calculator, again, 11 degrees of freedom, and then the area to the right of my value should be 0.025. So again, 0.025 is over here. So the t-score is going to be 2.0200, what was that, 9852. If we round, this will be 2.201. So let's write this down. So my t-score for my alpha, 0.05 divided by 2, is going to be 2.201, where the degrees of freedom is equal to 11. Cool. There is one other way to calculate this, and this is to use a table. So let me bring this up. If we're looking at an example problem, it may give you a t-distribution table to use as well. You can also go into StatCrunch to do this, but here's how we would use a table. This is what the table will look like. I apologize if it's small on the screen. But along the left-hand side and the right-hand side, we can see the degrees of freedom. So we'll come down to the degree of freedom 11. And then there's a few numbers in the middle. So what we want to do is identify which number here do we want. And there are two numbers, there are two column headings. Here I'm going to look at the area in the two tails. So if I scroll down to this picture over here, in the two tails, we're splitting up the area. So the total area in those two tails should be 0.05 because I'm looking at a 95% confidence interval. So the area in my two tails is 0.005. Come down to degree of freedom 11, 2.201, which is the same as what we calculated before.